Okay, so we come back to whatever we were doing. I hope you remember. So this is actually the general version of the theorem, that there exists a positive complete measure. Complete is important. Complete simply basically means that you are working on such a sigma algebra that if measure of a set is 0, then any subset of it, which of course have measure 0 by monotonicity, also belongs to the sigma algebra. That is very important. That is what complete means. So the theorem says that there exists a positive complete measure M on RT defined on a sigma algebra M, and the kind of positive linear functional we have dealt with, which is basically the Riemann integral, gives rise to this M by this representation theorem. This sigma algebra is called the Lebesgue sigma algebra, which has a much simpler description, which I will tell you later. But the first important property is that Lebesgue measure, this M is called the Lebesgue measure. So this M is called the Lebesgue measure. Which comes out of the Riemann integration, thought of as a positive linear functional. That measure of any rectangle is actually the volume of this rectangle. And that we have actually proved in the last lecture for one dimension. I'm going to prove the whole theorem only in for one dimension. Now, if you look at the second property, this B subset of M basically means that the Borel sigma algebra sits inside M. So let me note it here. B stands for the Borel sigma algebra. And that follows from Riesz representation theorem. We don't have to prove anything. The general version of Riesz representation theorem says that all Borel sets are in the sigma algebra. So in particular, it is for this sigma algebra M, the Lebesgue sigma algebra. So it follows that Lebesgue sigma algebra is bigger than the Borel sigma algebra. Question is whether does it have extra sets? We will come to that question. The answer is yes. Lebesgue sigma algebra is actually huge. However, it gives you a criteria that a set is in the Lebesgue sigma algebra. These sets are called Lebesgue measurable sets if it is an element of the sigma algebra, Lebesgue sigma algebra M. The if and only if criteria is that E is sandwiched between A and B. A is F sigma, B is G delta, and measure of B minus A is actually 0. And this, we don't have to prove anything. It comes straight away from the Riesz representation theorem. So what we need to do today is basically to prove C, D, and E. The property C is called translation invariance. Now, why does it come? You can actually quickly observe it from part A. For example, if you have a rectangle W, and if you translate this rectangle by an X, it is still a rectangle, right? Yes. Can you hear me? Am I audible?
Yes, sir. Yes.
So I was saying that if you have a rectangle W, and if you translate by an X, that is still a rectangle, right?
Right.
So measure of W, which is volume W, is same as volume of W plus X because it's a rectangle. And then that is measure of W plus X by property A. So translation invariance, I'm trying to say, is actually already true for all rectangles. That follows from property A. Are you convinced? Okay, we'll come to that again. So we start proving C. Then we prove D, then we prove E, and so on. Okay, so proof of C. So we prove C now. The proof is actually easy. To prove C, I will make a statement. Let us see whether you agree with me or not. I am saying that it suffices to prove prove that measure of what should I say? Measure of Q equals to measure of Q plus X, where X is fixed in R, because we are proving everything in one dimension. What is Q? For all 2 to the power minus n cubes. Mind you, I am on real line, so I am working for d equals to 1. Then a particular Q actually looks like, can anybody tell me what a 2 to the power minus n cube in one dimension look like?
M by 2 to the power n, comma m plus 1 by 2 to the power n. Okay.
Exactly. K by 2 to the power n, then k plus 1 by 2 to the power. These are typical cubes, whereas k will vary because I want it to be proved for all q, and also n will vary. All natural numbers. Now, can anybody tell me why it suffices? Mind you, what is your statement of C? Let us have a look back at it. C says that em of E plus X is measure of E for all X. What is E? So let me write that down for you. What is E? Well, it should be true for all E in M. I'm saying it suffices to prove it only for 2 to the power minus n cubes. Why? Well, the situation is something like this. If I prove the translation invariance for all 2 to the power minus n cubes, let's look back. This is what I want to prove. Which one? Let me try to mark it. This is what I want to prove. But suppose I prove this, what happens then? Take any open set. Then any open set is countable disjoint union of 2 to the power minus n cubes for various n's, correct? So take any open set V. That was a fundamental result we have proved earlier. So take any V open. Then what do we know about V? Well, we know that then V is union some I from 1 to infinity Qi, where all these Qi's are 2 to the power minus n cubes, one dimension, various n varying, and most importantly, this is a disjoint union. This is a result we have actually proved in one dimension, right?
Yes, sir.
Agreed? So what is then your V plus X? This is simply union I from 1 to infinity Qi plus X. Since Qi's are disjoint, Qi plus X is also disjoint because X is fixed. X is not varying. So if you like, I can call it X naught, a fixed X naught I'm talking about. Now, since this is a disjoint union, then measure of V plus X naught is equals to summation I from 1 to infinity measure of Qi plus X naught. Mind you, now Qi is a cube. It's an interval in one dimension. In general, it's a cube. But measure of a rectangle is same as volume of the rectangle. In one dimension, measure of an interval is the length of the interval. So I can write this as summation I from 1 to infinity length by A Qi plus X. This is by A. But now, if you have an interval, a semi-open interval, which is actually of this form, all these QIs are of this form. If you translate it by x naught, does its length change?
No, sir.
No, sir.
So that means you are actually saying that this x naught has no value, right? I can drop it. So you are basically saying that this is same as length of QI. Right? Now, again, I can apply A by saying that this length is nothing but the measure. So it's I from 1 to infinity, actually Lebesgue measure of QI in one dimension. Same thing happens in higher dimension. And then you write it as measure of, because these are disjoint, I from 1 to infinity QI. But that is nothing but measure of V. So this proves C for open sets. That for open sets, it's translation invariant. Now, can you tell me whether this is now true for all Lebesgue measurable sets? That is all sets which are in M. Well, that is pretty easy by definition, and that is the game of regularity. So suppose E is in M. That means E, by definition, is infimum of the measures of open sets which contain E. So E subset of B, B open. And then what do I know about? If all these V's are covering E, that means V plus X naught will cover E plus X naught. So measure of E plus X naught, again by definition, because it is in the sigma algebra, it is infimum of measure of V plus X naught. Where I can actually write that E plus X naught is sitting inside V plus X naught. If V is open, is V plus X naught open?
Yes, sir.
Yes, sir.
Because translating by X naught is a homeomorphism of real line. And conversely, if V plus X naught is open, then so is V by subtracting X naught. Now, I already know measure of V plus X naught is measure of V. In the previous step, I have proved it. So it is infimum of measure of V. V subset of E, V open. So which regularity I have used?
Outer regularity.
Exactly. This is then measure of E. That is why you need regularity. So this proves C for us. Excellent. So C has been proved. So basically, as I said, now perhaps on hindsight, you realize that this translation invariance works because measure of an interval is length and translate of an interval is interval. The length doesn't change. So the fundamental step is to know that the translation invariance actually happens for all 2 to the power minus n cubes. If it happens for cubes, then it has to happen for open sets because they are disjoint union of cubes. And if it happens for open sets, it will happen for all sets by outer regularity. That is the principle. And that's why I said it is important to notice that this translation invariance property is actually true for these guys. Everything is coming from here because cubes are certain forms of rectangles. Okay, we now try to prove D. So let us look back at the statement of D. D says that suppose a positive translation invariant Borel measure is given to you. That means it is defined on the Borel sigma algebra. So now I don't know anything about the Lebesgue sigma algebra. It has one additional property. First of all, it is translation invariant that is given to you. And it is also given to you that measure of K is finite for all compact subsets. Then there exists a positive real number C such that measure of E is constant times the Lebesgue measure. We are proving it in one dimension. Now, can you tell me why this property has been added? Why it is so important to have measures of compact sets are finite? Anybody?
Because we can apply RRT maybe.
No. The point is, just let's have a discussion here, a small discussion. So on the Borel sigma algebra, suppose you define a measure nu such that nu of E is infinity for all E in P. Now tell me, is this measure nu? Is this a measure? First of all, will it be a countably additive set function?
Yes.
Because everything is infinity. Is this translation invariant?
Yes.
Is it a constant multiple of the Lebesgue measure?
Yes. Infinity.
What C are you working with? So
Yeah.
what is nu of 0, 1 should be equals to C times Lebesgue measure of 0, 1, which is 1. So that means your C has to be equals to infinity, right?
Yes.
But that is not allowed. There exists a positive real number C, we said. So this measure will not do. So you don't want this measure to come in the scenario. So you have to stop that. So you have to put certain condition on this nu. So what kind of a condition you would like to put? Well, the kind of condition which Lebesgue measure has. Any compact set is a closed and bounded subset of Lebesgue measure. So Lebesgue measure of any compact set is finite. And you want your measure to be a constant multiple of Lebesgue measure. So you must put some analogous property. And that analogous property is this. You put that measure of any compact set is finite. Then it turns out that the measure is a constant multiple of the Lebesgue measure. Am I clear that why this condition has been added?
Yes, sir.
It's a very important property, otherwise we will be in deep trouble. Okay. So let's try to prove this property D. I'm going to use something called, instead of Q omega n, I'm going to use something called omega 0, Q0 and things like that, which I haven't used earlier. So let us say Q0 be 2 to the power minus 0 cube. What a funny language. What does this mean? Implies this is actually a 1 cube. So what does it look like? Q0 looks like K by 2 to the power 0, K plus 1 by 2 to the power 0. I know I'm writing something very funny, but it is just to make things identical with this. That means instead of natural numbers, now I am using 0 union natural numbers. Okay. So this is, of course, we have understood it by now. What I mean is K plus 1. That means intervals of length 1 with left-hand point on the set of integers. That I am keeping. K is in Z. Is it clear to everybody that instead of omega n, now I'm actually looking at omega 0. We are actually looking at omega 0. All of you remember what was omega n? It was all semi-open intervals of length 1 by 2 to the power n. The left end point is of the form K by 2 to the power n. So if you look at omega 0, it would include all intervals of the form K by 2 to the power 0, K plus 1 by 2 to the power 0, that is K plus 1. Let's call this Q0 for a fixed K. Okay? Okay so far?
Yes, sir.
Now
Yes, sir.
let me do the following elementary arithmetic. K plus 1. Look at it very carefully what I'm doing. I write this as union S from 0 to 2 to the power n minus 1. Again, semi-open interval, K 2 to the power n. This is a trick I have used time and again. 2 to the power n plus S by 2 to the power n, comma, K 2 to the power n by 2 to the power n plus S plus 1 by 2 to the power n. Do you agree to this writing? What am I doing actually? Pictorially speaking, what I am doing is simply the following. This is K. This is K plus 1. Choose any n. Break it into equal pieces such that everybody has length 1 by 2 to the power n. That is all. This is what I have done. Is this clear? For example, if you put S equal to 0, can you tell me which point you get? On the left side, if you put S equal to 0, what is the left endpoint?
K, comma,
Correct.
K
Correct.
plus 1 by 2 to the n.
Right. Left endpoint is K, that you agree, right? If I put S equal to 0.
Yes.
Now, put S equal to 2 to the power n minus 1 and tell me what is the right endpoint.
K plus 1.
That means the whole interval K plus 1 has been broken into disjoint pieces, correct? Where every subinterval has length 1 by 2 to the power n. Because
Yes.
this subinterval,
Yes,
if you
sir.
look at, its length is 1 by 2 to the power n, correct? And that is what is the picture it looks like. That is what I have written below. Okay. Now, since we agree to this, let's assume that mu, the measure which we have started with, which is translation invariant and finite on compact sets, let's assume mu of Q0 equals to some number, call it C. Is C a finite real number or is it infinity? What is your Q0? It is written at the top. This Q0 actually sits inside the closed interval Kk plus 1, which is a compact set, correct? And hence, measure of Kk plus 1 is finite because it's a compact set, and that is the condition on the measure. So mu of Q0 is smaller, and hence in particular it is finite. I don't know what it is. Let's call it C. Are you having any confusion why I am not saying measure of Q0 equals to 1? Why I called it C? Can anybody tell me? Why not mu of Q0 equals to 1? Let us look back at the statement, what we are trying to prove. We again look back at the statement. It is D we are trying to prove, okay? D says, suppose mu is a positive translation invariant measure. Nobody said that this is Lebesgue measure. So I don't know whether mu assigns to an interval its length. That is something which Lebesgue measure does, but mu is any measure which is just positive translation invariant and measure of compact set is finite. So mu is not Lebesgue measure. I don't know that, right? So can anybody now answer my question that why not mu of q0 equal to 1? Well, the answer is because nobody said that mu is Lebesgue measure. It's just any measure. All I know that measure of q0 has to be finite. So that finite number I call C. Okay. But it is given to me that mu is a measure. Okay. So what I can write is that C, that is measure of kk plus 1, because that is what q0 is. And since it's a measure, it is countably additive. So that means this is equal to summation S from 0 to 2 to the power n minus 1 measure of this ugly looking interval. Let's write that k2 to the power n by 2 to the power n plus s by 2 to the power n, comma. I write this one in a slightly different way. K2 to the power n by 2 to the power n plus 1 by 2 to the power n plus s by 2 to the power n. I write it in this fashion. Okay. The next line I write in a slightly better way. You will see that what I am driving at. This is s from 0 to 2 to the power n minus 1. No problem with that. Measure of k2 to the power n by 2 to the power n plus, comma, it is k2 to the power n plus 1 by 2 to the power n plus s by 2 to the power n. Translation of this interval. Agreed?
Yes, sir.
But the measure mu is assumed to be translation invariant. If you translate, the measure doesn't change. That means this s by 2 to the power n term, I can forget. I'm still inside the sum. So I'm saying I'm going to delete this term because it doesn't change the measure, because the measure is assumed to be translation invariant. Agreed? So I can drop this term.
Yes, sir.
Let's drop it. Now I'm standing here. Okay. I see. So this is then, how many terms are here? You see that now the terms are free of s. There is no s. S is gone. So how many terms are here? Each term is same. How many terms here?
2 to the power n.
2 to the power n terms times mu of, now I write in a simpler form. I write it as k, then k plus 1 by 2 to the power n. This is what I get. It then follows, what do I get by all this circus? I get that this implies that mu of k plus 1 by 2 to the power n, the measure of this set is actually 2 to the power minus n times measure of kk plus 1, which is C. So it is C. Okay. So all I have done is I have taken this from here to here. Okay. But then I can write this as C times Lebesgue measure of k plus 1 by 2 to the power n. Because that is the length of this interval. So this implies then that mu of q equals to a constant multiple of m of q. And this is true now for all 2 to the power minus n cubes. Right? Because they are of the form k plus 1 by 2 to the power n, where I'm not saying k is an integer really. It could be of the form k by 2 to the power s. Now this, since it is true for all 2 to the power n cubes, this implies measure of v is again c times Lebesgue measure of v for all v open. Okay, so this then implies that measure of E is equals to some constant times measure of E for all E belonging to the Borel sigma algebra by outer regularity. And this is exactly what we wanted to prove. Okay, agreed. Any problem?
Sir,
Yes.
sir, I have a doubt, sir. Can we take mu of q naught to be 0?
Mu of q naught to be equals to 0. That would be a big problem. Actually, no. Can anybody answer his question? It's a very good question. That I have taken it to be C to be strictly bigger than 0. Suppose I take C to be equals to 0. Then what happens is I have to change the statement of my theorem. If I do that, then I have to include C is bigger than or equals to 0. Okay, that we are not allowing. If you take C to be equal to 0, come back here. Suppose your C is equals to 0. What will happen is you will get that this C is equal to 0. This C is equals to 0. This C is equals to 0. Strictly bigger than 0 will not work then. Okay?
Okay, sir.
Because if you take kk plus 1's measure to be equals to 0, then inside it there are open sets which will have measure 0. You don't want to have that. Okay?
Yes.
Okay. The theorem will still be true, but then your C will turn out to be equals to 0. Okay. We now want to prove the last part, E. Okay. So what was T in the one-dimensional case? It's a linear map. So Tx must be equals to alpha x or some real number alpha. That could be 0. So if T equals to 0, then what happens is, then M of TE, that is also equals to 0. Why? Are we saying that Lebesgue measure of a single point 0 is 0? I'm saying yes. Take any point x0 in R. I claim that implies that Lebesgue measure of x0 is 0, which is actually obvious. Why? Because this set point x0 as a set is sitting inside x0 minus 1 by n, x0 plus 1 by n. That means Lebesgue measure of the singleton set x0 is less or equals to measure of the set x0 minus 1 by n, x0 plus 1. But I know that Lebesgue measure of any interval is its length. One has to be very careful here. I'm not saying measure of an interval is length. No, there are various measures. I'm saying Lebesgue measure of an interval is length. M is the Lebesgue measure. So it's 1 by 2n, which goes to 0. That means measure of every singleton is 0. So it also implies Lebesgue measure of every countable set is 0. So in particular, measure of 0 is 0, which is this statement. Can you tell me, given any countable set, is it in the Borel sigma algebra or not?
Yes, it is F sigma set, so it is in Borel sigma algebra.
Yes. Okay. So measure of t then is 0. In that case, you choose your delta t to be equals to 0. So take delta t equals to 0 to get measure of TE equals to delta t times measure of. The next case is when alpha is t is non-zero. Now t is non-zero is same as saying alpha is non-zero. Okay. Now I look at this measure mu of E. I'm defining it to be equals to Lebesgue measure of TE. Okay. It of course defines a measure. It defines a measure. That is easy to check. Not only that, what is mu of E plus x? Say x naught. It is Lebesgue measure of T of E plus x naught by definition. But T is linear, so it's Lebesgue measure of TE plus Tx naught, because it's a linear map. But Lebesgue measure is translation invariant. So this is equals to measure of TE. But that, according to my definition, is mu of E. This is true for all x naught in R. So my measure mu is translation invariant. Is it finite on compact sets? So take K compact. Look at mu of K. That is then Lebesgue measure of Tk. But T is simply multiplication by alpha. So it's a homeomorphism of real line. So Tk is compact if K is compact. And Lebesgue measure of any compact set is finite. Now I can actually apply D. So by D, this mu must be a constant multiple of Lebesgue measure. So there exists C bigger than 0 such that mu of E is C times M of E. But what is mu of E? That is M of TE. So it is C times measure. Now, if measure of E is non-zero, if I choose some such E, so if I choose E in the sigma algebra such that measure of E is bigger than 0, then I can actually find out value of C. And that's what I'm interested to find out. This is a theorem which is actually difficult in higher dimension. Anyway, in one-dimensional case, then C is measure of TE divided by measure of E. So now I want to choose E properly. So simply choose E to be equals to the, say, open interval 0. Can you tell me what is, okay, choose this. Assume alpha bigger than 0. Can you tell me what is TE? What was T?
Open interval.
Let's look at the definition of T. It's given here. So can anybody tell me what is TE?
Open interval 0 alpha.
Excellent. Open interval 0 alpha. And what is measure of E? That is 1, right?
Yes.
So what is measure of TE by measure of
Alpha.
alpha? Correct. So C is alpha in this case, which is equals to C. And let's now look at alpha less than 0. If alpha is less than 0, can anybody tell me what is TE?
Minus alpha comma 0.
Alpha is negative. Minus alpha will be positive.
Yes, alpha comma 0.
Alpha. So what is measure of TE?
Alpha.
No,
Mod alpha.
Mod alpha.
right?
Right.
And measure of E is 1. This is my C. This C I call delta T. So now I know this delta T is actually turning out to be mod alpha. Right? In general, in higher dimension, in general, so let's just make this comment. I'm not proving it. That is difficult to prove. That in general, for D bigger than 1, if what should I say? If dimension of the range T is strictly less than D, then delta T is C. In one dimension, what it is correspond to?
Dimension of a point is 0. Measure of a point is 0.
What does it say about alpha? You are on one dimensional space. So dimension of range T is either 1 or 0. But your Tx has to be of the form alpha x. So what does it say about alpha then? If this case has to occur in one dimension.
1.
0.
0.
Alpha
Yes,
equals to 0 case. So we did get C equal to 0 in that case. So that is one. Important is the next case, that if, and this is hard to prove, if dimension of the range T, it's not easy, is exactly equal to T, then your delta T turns out to be equals to modulus of the determinant of T. In one dimension, what it is? If your Tx equals to alpha x, determinant is product of the eigenvalues.
So it will be mod alpha.
This is exactly what has happened. This is the one-dimensional case. In higher dimension, it is slightly difficult to prove. Okay. Now, so this completes the proof of the theorem. I now want to make several comments there is something called Lusin's theorem, which we will discuss probably in the tutorial. I will write down things and Professor Sahani can then tell you about it. But there are some comments I want to make. These are all comments. So number one, as I said, M is called Lebesgue measure. It has the property that the measure of any open set is positive, because inside any open set an interval is sitting. So measure of any open set is positive. Not only that, measure of any translation invariant measure, which is finite on compact sets, those measures being constant multiple of Lebesgue measure will also have the same property, that measure of any open set is non-zero. It's strictly bigger than zero. Okay. One question one usually has, that whether the Borel sigma algebra B and the Lebesgue sigma algebra M, what is the comparison between these two? The comparison is the following, that if E is in M, then there is an F sigma set, which then is a Borel set, it is F sigma, such that your E is A union another set F, such that measure of F is 0. So measured theoretically, the difference between a Lebesgue measurable set and a Borel set is always a set of measure 0. However, one thing we anyway know, that the Borel sigma algebra is sitting inside the Lebesgue sigma algebra. But how big is the Lebesgue sigma algebra, or is the containment strict? This kind of questions one can ask. I'll come to that. Actually, one can show the following, that if you define C to be equals to the cardinality of the reals, it's not very hard, but time-taking proof. If C is the cardinality of reals, the cardinality of the Borel sigma algebra, that is the number of sets, roughly speaking, sitting inside the Borel sigma algebra, is exactly equal to C. On the other hand, one shows, and that's a very important thing, that there exists an E inside the Lebesgue sigma algebra, such that E is uncountable. It is uncountable, and Lebesgue measure of this set is 0. But the moment you are saying measure of E is 0, then any subset of E is also of measure 0, and they belong to the Lebesgue sigma algebra, not necessarily to the Borel sigma algebra. Actually, this E, which one can construct, is the so-called Cantor's middle third set. This is actually a Borel set, but it has got huge number of subsets which has got measure 0, and hence they are sitting inside the Lebesgue sigma algebra because the measure is complete. It follows then that the cardinality of the Lebesgue sigma algebra is at least 2 to the power C, and hence it is strictly bigger than C. So Lebesgue sigma algebra has many sets which are not in the Borel sigma algebra. Okay. That is one comment. So Lebesgue sigma algebra is basically very small compared to the Lebesgue sigma algebra, but measured theoretically it is not really very small. The difference is only a set of measure 0. Most important comment is the following: the way we have defined the positive linear functional, I want to come to that. So if d equals to 1, it's actually true for any d, but I'm writing it for d equals to 1. It's clear from the construction of the positive linear functional called big lambda and Riesz representation theorem that the following holds true, that I know that this positive linear functional is given by a measure. That measure is the Lebesgue measure. So this much I know, that lambda f is nothing but integration over R, fx dmx, the so-called Lebesgue integration with respect to this measure. But all of you know how this lambda f was defined. It was simply the Riemann integral of the function. That means it is also integration fx dx. I don't write dmx here. So the claim is, what it follows, that for all compactly supported real valued continuous functions, Riemann integration and Lebesgue integration are same. And so are their integrals. So if f belongs to CCR and is real valued, complex valued is not a very holy thing. They are also the thing are same, but I'm not talking about that. So if f is a compactly supported continuous function, then Lebesgue and Riemann are same. So the chance is there are many more functions which are Lebesgue integrable, but not Riemann integrable. And that we can now very easily see. So consider this function. Fx equals to 1, 0, lesser equals to x, lesser equals to 1, and x irrational. Equals to 0 if 0 lesser equals to x, lesser equals to 1, and x rational. This is basically a lengthy way of writing that I am looking at the indicator function of all the irrational numbers in closed interval 0. Now everybody knows that f is not Riemann integrable. Can anybody tell me whether f is Lebesgue integrable?
Yes, because measure of all rational numbers equal to 0.
Measure of all rational numbers is equals to 0. So what? When Professor Sarkar taught you Lebesgue integration with respect to an abstract measure, I'm sure the first thing he said that indicator function of a measurable set has Lebesgue integral to be equals to measure of the set, right? He must
Yes.
have done
Yes.
that.
Yes.
That integration chi ax, integration over x, the measure space, d mu x is measure of the set. That is the first assumption one starts with, right? Let's apply the same funda here. So can anybody tell me what is integration over R, fx dmx? Quick.
Measure of E.
Measure of E. Lebesgue measure of E is the right word perhaps, because we are doing Lebesgue integration. I mean, we should make a distinction, be very clear about it in your mind, that Lebesgue integration has got absolutely nothing to do with Lebesgue measure. Lebesgue integration can be done with respect to any measure. It's a method of doing integration with respect to a measure. What we are doing here is we are doing Lebesgue integration with respect to the Lebesgue measure. So measure of E is the correct answer. But what is measure of E? Can anybody tell me what is measure of E?
1.
That's 1. So the function is not Riemann integrable, but Lebesgue integrable. That means the method of integral seems to be generalizing Riemann. Generalizing because this. For CC, it's all same. In fact, one can go slightly further, that suppose you have a function f belongs to RAB, that is the space of all Riemann integrable functions. What you can do is you define gx to be equals to 0 if 0 strictly less a, or sorry, if x strictly less a, or x strictly bigger b, and equals to fx. if x is in A. You can very easily show that this function is Lebesgue measurable, and the Lebesgue integration over R of gx dmx is actually Riemann integration of the function a to b fx dx. If I already assume that f to be Riemann integral. Now, in many cases, what one can do is one doesn't want to work with whole of real line. So what they can do is sometimes, and that may appear in the next series of lectures, that given a measure mu, let us say on the Borel sigma algebra of RT, I'm on real line, say on R, take an interval AB and define a new measure called mu tilde of E to be equals to mu of E intersection AB. Okay, this means restricting the measure on this closed interval. And this whole machinery, whatever we have described and talked about on whole real line, will work on this AB also. Okay. So the what is the sigma algebra? Well, restriction of the Borel sigma algebra on closed interval AB. That will give you rise to a new sigma algebra. And on that sigma algebra, you can talk about mu tilde and you can talk about Lebesgue integration with respect to this measure. Is there any other point I wanted to mention? It is there in my lecture 5. What is a measurable function that you anyway know that Professor Sarkar must have talked about, that you have a sigma algebra, then look at a function where inverse image of open sets are in the sigma algebra, then it is called the measurable function. So analogously, if you have functions f from say real line with Lebesgue sigma algebra to C, satisfying the property that f inverse of u belongs to M for all u open in C, I should write capital U, open in C, then f is called Lebesgue measurable. Similarly, if you have Borel sigma algebra instead of the Lebesgue sigma algebra, then under the analogous definition, f is called Borel measurable. Okay, thank you everybody. This is where I stop. My time ends now. I will just send one set of tutorial which will deal with something called Lusin's theorem. Okay. So any questions you can ask me. So this ends my set of lectures. Thank you.
Swagato, thanks so much for this set of lectures. I've been sort of sneaking in and listening.
Okay.
It's been so pleasant to hear you talking about these things.
Okay. Thank you very much. I will call you soon for some questions.
Yeah, sure. That would be good. Yeah.
Okay. Bye then. My time is up.
Thanks so much.
Okay. Bye.